Okay, nice. You can begin. Thanks, Kishor.
Okay, thank you. So so as like Kianvi mentioned, I mean, so initially, like, these were supposed to be given, like, internally, but then we thought, like, maybe it's good to, like, make it open to everyone. And it seems there are around 60 plus people. So yeah, like, I hope I don't disappoint you. So basically, yeah, like, I will talk about, like, quantum error correction. And so normally I like to, like, take questions in between, but here I need to, like, cover in 6 sessions all the content. And I would like to take question in between. Maybe, like, somebody can post that in the chat. And I would prefer, like, if other people, if they know the answer, like, maybe they could respond. So in this way, like, I may be able to, like, finish what I have decided. But yeah, I mean, we could discuss more in, with time remains and all. Yeah, in the end. Yeah. So okay, so as you can see, like, here, yeah, it works. Fine. Awesome. So you can see, like,
Kishor, do you plan to record this?
Yeah, it's being recorded.
Okay.
Yeah. Okay. So so yeah, I mean, so currently I am at A Star, like, which is a national lab in Singapore, and so I work at IHPC there, and yeah, like, primarily my research interests have been, like, quantum machine learning, device certification. Yeah, but recently, like, we moved into, like, error correction out. And so, like, this, like, series of tutorials, they will be later, like, posted on QuantumGrad. So like, I mean, also on QuantumGrad. So it's like, I will explain, like, what QuantumGrad is, like, yeah. So this is the schedule. Like, I mean, there are, like, this series of like, the 6 tutorials, and I think many of you already know the content. And, like, when it comes to, like, references, I mean, I will follow mostly, like, Dan Brown notes here, and also, like, some of the chapters from this book on quantum error correction. Here, like, I mean, sometimes I also, like, for some of the parts, I will also, like, use papers from archive. So, I mean, there are many papers, so it's not possible to list also, like, I mean, you can basically search them. And, like, when it's required, I will make a reference to them. Okay. Nice. So there is a bit of promotion here. One thing about this QuantumGrad. So QuantumGrad, like, I recently came to know about it. So, like, basically, yeah, like, so Sanjay Vishwakarma from IBM Quantum, he and others, like, they're involved in this nice, I would say, they call it one-stop solution. Basically, it's an open source platform where, like, the content related to, like, quantum computing is present. And yeah, I mean, it's I think open source and everybody can access and all. And these like, tutorials, they will be later also hosted at QuantumGrad. So if you want to, like, I mean, yeah, like, get more information and all, maybe, like, I think it's a good idea to maybe, like, subscribe. On the side, like, I would like to just mention that if you are attending APS March meeting, there is this work where I'm involved. So you can see me here with my old affiliation, and it's on hyperbolic flocate quantum error correcting codes. Like, so it's with like, like, basically my friends and colleagues in Maryland. And yeah, like, if you are if you are attending APS, then please feel free to, like, attend, and yeah, like, you might like it. Okay, so we all know that, like, the current era is basically, like, the NISQ era, and it's called, like, noisy intermediate scale quantum era. Like, I mean, if you expanded. And there have already been four experiments, and 2 experiments from USTC group. And but so far, first of all, how powerful these experiments were, in terms of classical simulability, that's still debatable. And then on top of that, the practical utility of these experiments is, I would say, contested. I saw one paper just 3 days back by Sheehan and Scott Aronson. But I mean, so far the consensus is that with the NIST devices, we do not know any practical application here. So you can see that there is review which I would just mention here, and the word NIST which was proposed by John Preskill, and basically there have been a lot of work, and you can see our review with some of the friends and colleagues. And you can see here I have put this recent this paragraph from this recent experiment by Google, where they say that currently in this recent experiment on the Sycamore processor, the errors are between 1 in 10,000 to 1 in 100. And we will need rates in the range of 1 in 10 to the power 9 to this much to run quantum circuit that can solve industrially relevant problems. So, I mean, to reach there, I think it will be important to, perform quantum error correction, and maybe, for noise suppression, I think it will be quite important. So, so it very much elucidates, the importance of quantum error correction for the community. And then on top of that, there are many other motivations also. So, it has relations with, general theory of relativity, basically black hole physics, and then many body physics. Then there was recently a breakthrough in theoretical computer science, which used a kind of error correcting codes called quantum LDPC codes. And then also in metrology, there have been a series of papers which have looked at how quantum error correction can improve metrology. Nice. So there have been a series of works, and it makes sense that we should understand quantum error correction, if we are interested in any of these topics. Okay, so today I will focus on, basically there are 3 parts. The first part will be the classical code, which will be a classical 3-bit repetition code, and then I will move to a quantum 3-bit repetition code, and finally I will talk about a stabilizer formalism and show you that how you can understand the quantum 3-bit repetition code in the stabilizer formalism. So this part is, you could many of you might find it elementary, but in the later tutorials, when we talk about Tori code and others, it will build on, So, yeah, I apologize if some of the content here, may look elementary, but I think it will gradually, pick some pace. So let's look at, the simplest starting point when we think about, classical code is the classical 3-bit repetition code. So what is this classical 3-bit repetition code? It basically encodes bits by repeating them, and 3-bit basically means that it repeats it 3 times. So you take 0 and, and you write it 3 times, and, you get this 0 logical. And if you repeat 1 3 times, you get 1 logical. So we have the 0 logical here, and we have the 1 logical here. So these are the code words. Now, the error which can happen in classical code is a bit flip error. So your 0 can become 1, your 1 can become 0. So, for example, your 0 logical, like let's say if the first bit flips, then it can become 100. If the like for the one logical, it can become 011. And similarly, let's say if the last bit flips, 0 logical can become 001, and 1 logical can become 110. Example. And error detection here is like also quite simple. Basically, you look at your code strings, and if you see that the bits in the string are not identical, then it means some error has occurred. So how do you correct it? Like when you have detected an error? So that's also simple. Basically, you reset all the bits to majority value. So for example, if you have 0, 1, 0, you will write it as 0, 0, 0. Or if you, let's say you have 1, 0, 0, you will you will set it to 0, 0, 0. So basically, you will reset all the bits to whatever the majority value is. That's it. And then the question becomes like, what if let's say that there are three bits flip. So for example, let's say 0, 0, 0 flips to 1, 1, 1. Can you still detect the error? Now that is not possible to detect, right? Because here, as we mentioned before, the way you detect the error is by looking at whether the bits in the string are identical or not. And let's say if all three bits flip, then the bits are all identical, and you will not be able to detect it. So code distance captures this notion of whether you can detect the error or not. So code distance basically means the smallest number of bit flips required to transform any two code words into one another. So you have the two code words that we have are basically 0, 0, 0 and 1, 1, 1. And you need 3 bit flips to basically transform one code word into another. So for a 3-bit repetition code, the distance is 3. If you have an n-bit repetition code, the distance will be n. Okay. So there is this notion called Hamming distance, which captures the notion of distance for the classical code. So basically, let's say you have 2 bit string A and B. The minimum number of bit flips to transform bit string A to bit string B is called the Hamming distance between A and B. So you can see that basically if you have a bunch of code words, you need to calculate the minimum Hamming distance among all pairs of code words, and that will be your distance of the code. So everything. So you can see that the maximum number of errors which can be detected is obviously d minus 1, because if it's d, then the error detection scheme will not work. And the maximum number of errors that can be corrected, that will be d minus 1 by 2. Yeah. And why? Because otherwise your majority majority reset scheme will not work. So that's why the number of error that can be corrected is this floor of d minus 1 by 2, and the number of error that can be detected is basically d minus 1. So far we we talked about errors, code words, errors, just replacing so code words and then errors, and then what happens to code words after the error detection, correction, distance. Now you have let's say you have n number of bits in your code words, and let's say k is the number of encoded bits. So in our case, let's say the 3-bit repetition code, we are using 3 bits to encode 1 bit. And let's say d is the the code distance. So in our case, for the 3-bit repetition code, the distance is 3. So for such cases, you write it as, there is this notation in classical error correction, which write 313 basically. So this is your N, K, and D. And let's say instead, if you are interested in like N bit repetition code, it will become N11, N1N. So you are using basically N N bits to encode 1 bit, and your distance is N. Yeah, nice. So what are the logical operations on your code? Yeah, like let's say here the goal is to like perform the computation on the encoded information. Like you would like to perform some computation, like you have encoded, but there is you just do not want to store it. I mean, like you would like to perform some computation, and one of the computation, like is like they're applying the NOT bit. So the action will be same as like what you have in the unencoded case. So for example, if you apply the logical NOT gate on 000, it should send it to 111, and when you apply to 111, it should like send it to 000. So you see that your logical operation, they keep your they keep your code words, like they map one code word to another, like yeah. Okay, like here at least, yeah. So there is, I mean, later I will talk about this notion of code space, and I will tell you that this logical operation basically, keep the state within the code space. Yeah. So I mean, so for the moment, like we just discussed the classical 3-bit, or you could say, like N-bit repetition code, where we talked about, like the encoding, the error, yeah, like and the distance, NKD notation, the logical operations, and so on. So this completes the classical part. Let's look at the quantum part now. So now we look at the quantum 3-bit repetition code. So here, like similar to the classical case, we have your 0 logical will be like 0 0 0. The 1 logical will be 1 1 1. Yeah, like basically repeat it. And so which means that like let's say you have some quantum state alpha 0 plus beta 1, you will encode it as alpha 0 0 0 plus beta 1 1 1. So you can see that like the here like this all possible like psi that you have here belongs to the span of 0 logical and 1 logical, like which we have defined here. So this is your code space, and basically error-free encoding of a quantum state it lies in this subspace. Yeah. So I think this makes sense. So that's how like similar to the classical case, we have defined the code word for the quantum case. Now let's look at the errors. So here you can have like bit flip error or a phase flip error. So a bit flip error basically like we know that it takes your x, like when like is denoted by x, it like takes your 0 to 1 and 1 to 0. So that it's given by this matrix like 0 1 1 0. And when you act it on 1 0, it will give you 0 1, and when you act it on 0 1, it gives you 1 0. And the phase flip error basically like it's just like it just adds sorry. So yeah, so it just adds a phase in front of like 1. Yeah. So if both X and Z error can be corrected, more general errors can be corrected as well. So this you can think about like basically, even though the quantum errors can be continuous, like by just like looking at your X and Z error, you can like, so basically it's a way to discretize quantum errors, and you can like correct more general errors as well. Yeah. So so we talked about errors. So like I mean, so unlike the previous case, we don't only have like bit flip error, but we also have this phase flip error. Nice. Now what happened to the encoded state after a single bit flip error, for example? So since we are looking at repetition code, we will like we will be interested in like bit flip error. So let's say the logical state that we had was alpha 0 0 0 plus beta 1 1 1. Now let's say like you act let's say the second bit, the bit flip error happens on the second qubit. So it will just, flip your second qubit. So you will get 0, 1, 0 plus beta 1, 0, 1. Nice. So now again, the same question comes, okay, like some error has occurred and can you detect it? Now in quantum case, the situation is a bit tricky because you should not, I mean, if you try to measure the individual qubits in the computational basis, you will detect the error, but it will result in the collapse of the encoded qubit. So we don't want that. I mean, we want to protect the information, right? So the idea is that you measure symmetries of the state rather than individual bits. And one example could be, like a parity of any pair of bits. So the event parity, like something like 0, 0, 1, 1, odd parity, like 0, 1, 1, 0. So let's look at, like how it works. So for example, so this is a circuit which can be used to, let's say if you have any 2 qubit, this can be used to measure the parity. And this can be, shown to be as equivalent to measuring Z tensor Z on the first 2 qubit. You can work out the details, but let's look at, how this Z tensor Z capture, what we are interested in. So when you look at, 0, 0, the parity of 0, 0 is 0. And Z tensor Z, when it acts on it, it gives you, you get +1, right? And then Z tensor Z on 1, 1, that's also basically belong to the +1, subspace. On the other hand, 0, 1 and 1, 0, their parity is 1. And this belongs to, the -1 subspace. So you see that this Z tensor Z, basically it captures, it captures the parity of the pair of qubits, on which it acts. So here I have, this, I added this table, which, looks at, suppose the first bit, the error happens on the first bit. And when you act by, Z tensor I, you will get a -1, so because, the parity of the first and second bit, that will not be same. So that's why we have a -1 here. And this one also will give you -1, but, because these 2 bits are not top, I mean, this Z tensor Z, here no error has occurred, you will get +1, like Z tensor Z will not give you any error. Now it's crucial to see that as whenever your error, anti-commutes with the operator, that you are measuring, you get -1. On the other hand, when it commutes with the operator that you are measuring, it will give you +1. Nice. So this is the idea, you basically, you measure certain, symmetry, here the parity, and the object that you measure, for example, for the 3 qubit repetition code is basically Z tensor Zi, then Ziz and Izz, and that should, help you to detect the error. Nice. So finally, it becomes how do you correct the error? So to correct the error, basically you apply the inverse of the error operator, to just correct the error. So for example, if you have the xii, you just apply xii. And the reason is because, the polys are self-inverse. So because of that, error correction is quite easy in this case. Okay, so finally, we come to this notion of, what are the logical operations on encoded states. So we want basically, the logical operations X bar and Z bar, such that, similar to regular X, when X bar acts on 0 logical, it gives you 1 logical, and then it acts on 1 logical, it gives you 0 logical. Similarly, Z bar, when it gives you acts on 0 logical, it gives you 0 logical, but picks up a phase in the case of 1 logical. So one possible choice of X bar and Z bar that you could have is basically XXX and ZII. Why that is the case? You could see that when you have XXX and you act on 0, 0, 0, it will become 1, 1, 1. And similarly, if you act it on 1, 1, 1, it will become 0, 0, 0. So you see that this this acts as a nice choice of, logical X, like it satisfies the condition that we require. Similarly, like, for Z, maybe like, you could just select ZII, and you see that, like when you act it on 0, 0, 0, like it will give you 0, 0, 0. But when you act it on, sorry. When you act it on ZII on 1, 1, 1, it will give you minus 1, 1, because, like you have Z on one of the qubits. Yeah. So you see that this is this can act as, like as a, so at the moment we are just, we are not systematic, like just based on intuition, we are building, like what will be the logical operators, how will you, like detect the error. But later you will find that all these process can be automated, like using a simple idea of group theory. You can just, look at the problem. So finally, like here we look at this notion of distance of a quantum code. So here, like we define this notion of, like weight of an operator. So similar to the earlier case, in the earlier case, we had, the minimum number of bits required to, like we change one bit string to another bit string in the code space. Here, like we will use similar idea to define the distance, but like we will generalize it. And to generalize that, we use this notion of, like a weight of an operator. So weight of an operator is basically number of qubits it acts non-trivially on. So for example, XII, its weight is 1. ZZ, its weight is 3 because it acts non-trivially on 3 bits. And similarly, XXI, here the weight is 2. So the distance of a quantum code, like, is nothing but minimal weight of any non-identity encoded logical operator on the code, because that will take you, like one code word to another. And we are interested. So basically, if you think about it, so identity is not an error. But on the other hand, if let's say X or Z error occurs, like that can take your that can basically take your state outside the code space. Now, if you have if you have the number of single qubit errors that occur is equal to weight of a logical operator, then your state will remain inside the code space, but you will not be able to detect it. Similar to the case, the previous case where you had like 0, 0, 0, and let's say if you have, errors occurring at all 3 places, like you will not be able to detect it. So yeah, I mean, so the motivation is same as the classical case. You basically look at the minimal weight of any non-identity encoded logical operator on the code. So for the quantum, 3 qubit repetition code, the minimal weight of encoded X, if you look at, for the X, the minimal weight here is, 3, because like some of you are, I think, like I'm saying in the comments, you're writing like, why not IZZ, why not ZZZ? Like, I mean, there are many possibilities, but I'm saying, but for X, there is just one possibility, like XY is just XXX, like, just one possibility. But on the other hand, for the Z, if you look at the minimal weight of the encoded Z, this is 1. So the quantum 3 qubit repetition code can detect 2 X errors and no Z errors. And why that is the case? And then you can see it because, if let's say one Z error occur, it can take you, it can keep you inside the code space, and, you will not be able to detect it. Nice. So, and it makes sense because, this quantum 3 qubit repetition code is pretty much a classical. Nice. So to understand all this, like in a more systematic fashion, you could use something called stabilizer formalism. And And actually, most error correcting codes can be studied via the stabilizer formalism. So the idea is simple, like, I will explain later. And there are codes like, Shore code, Steen code, 5-qubit code, like CSS codes, Tori code, like planar surface code, like this can be studied, using this stabilizer formalism. And this is a formalism that is widely used to describe topological code. So later when I will talk about topology in one of the tutorials and topological code, you will see that, it very much related to stabilizer formalism. And it's a systematic approach to derive encoded logical operators. So you will see that the logical operator that we are interested in, that can be like, you can calculate that in a quite systematic fashion. So a stabilizer code, basically it's a tautological definition, is a quantum error correcting code that can be defined in the stabilizer formalism. And so basically to define a stabilizer codes, you need to specify two sets of operators, something called a stabilizer generators and the encoded logical operators. So we will see, what they are. So let's now look at the stabilizer group first, because we are talking about stabilizer generator. So let's psi j will, be the set of code word basis states. So like, for example, in the previous case, we had 0, 0, 0 and 1, 1, 1. These were the code word basis states. So let's say, in general, you have, this psi j, this set of code word basis state. And the stabilizer group is basically the set of poly operators which leave all code word basis states psi j invariant. Basically, let's say pk, so all those poly operators which act on psi j, I think this should be sum is, So basically all those poly operators which belong to a particular set and which, leave your code word basis states invariant, they will be called, the set will define a group called the stabilizer group. And the stabilizer operator or stabilizer element that will be a member of the stabilizer group. So there is a simple claim that, the set of stabilizer operators must commute. When you can in fact, show contradiction that, if they don't commute. So let's say you have two stabilizers, let's say S1 and S2, and let's say if they don't commute, then because we know that, since they are polys, so we will be interested in poly stabilizers. So they either commute or they anti-commute. So let's say if they don't commute, then we have S1, S2 equal to minus S2, S1. And let's say you have some state psi, which belongs to the, let's say psi j, which belongs to the code space. If you act on S1, S2, psi j, that will be nothing but psi j. But if you act on minus S2, S1 on psi j, that will be minus psi j. So you have this contradiction. And because of that, you can see that, they should, commute. Nice. Very good. So we talked about, the stabilizer group. Now for a group, and you can define, So for any group G, we are interested in all this. So we know that the stabilizer group is the element, the stabilizer elements, basically they commute. So it's a abelian group, and we know that any group G can be, specified by a set of generators, this Gj. And this theorem, which you can find in, regular, abstract algebra textbook, that if you have a abelian group of self-inverse operator, for example, polys are one such example, and poly stabilizers are one such example, then any element G can be written as, whatever this format, and you can, show that, using theorem that the order of the group G is nothing but, 2 to the power m, where m is number of generators. So one can use this, notion to basically come up with a simple formula. So let's say you have number of logical qubits that you have is k. the number of physical qubit that you have is n, and let's say m is the number of stabilizer generators. Then basically we know that the order of this group G is 2 to the power m, and so that's that's basically your code, so basically every stabilizer is dividing your Hilbert space in two parts, depending on whether you get the +1 eigenvalue or you get -1 eigenvalue. And the size of the entire Hilbert space is 2 to the power n, and you are basically dividing it m times. So so, and every time you divide it by half, you have 2 to the power m times that will be the final size of the Hilbert space, which which you will use as a code space. So that will be 2 to the power k. And then by taking log, you can you can instead see that this n is nothing but m plus k, and then from where you will get m equal to m minus k. So this simple relation you see. So for the moment, let's say even if it's becoming abstract, you can just see that we are talking about this formalism called stabilizer formalism, where we have a set of poly operators which which commute, and they leave a subspace basically invariant. And the elements of this this group, basically they are called stabilizer a stabilizer operator or a stabilizer elements. And then I just I just showed that basically the number of stabilizer generators that you have, it's related to number of physical qubit and number of logical qubits. So you can see that if you increase your number of stabilizer generators too much, your number of logical qubit may may decrease. Yeah. So let's look at the 3 qubit repetition code. So for the 3 qubit repetition code, the 0 logical is 0 0 0, 1 logical is 1 1 1. So the n is here 3, k is 1. So m is basically 3 minus 1 equal to 2. So you have 2 stabilizers here. And the order of the stabilizer group is basically 2 to the power 2, that is 4. And you can see that there are these 4 stabilizers which stabilize 0 0 0 and 1 1 1. Any element in the subspace. Yeah. So so basically, if you act on z z I on, let's say 0 0 0, you get again 0 0 0. Yeah. So we talked about so far, a stabilizer group and a stabilizer generators. Now the question becomes, how can you use this formalism to detect error? So we can detect errors on a stabilizer code by measuring the stabilizer operator. So let's say if your state is in the code space, then it should be stabilized by the stabilizer operator, which means it should correspond to +1 eigenvalue. On the other hand, if you measure it and you get -1 eigenvalue, you will find that something bad has happened. And in fact, you can just measure the stabilizer operators, and m measurements will suffice, and that should follow from the previous relation which I mentioned here. And since m is n minus k, you see that your m basically scales linearly with m. So the number of measurements that you need to perform, it scales linearly with the number of physical qubits, which is good. And normally, in the quantum error correction lingo, people talk something called syndrome, which is outcome of the measurement of a given stabilizer generator. So you have m stabilizer generator, and corresponding to that, you will have a bunch of 1 1 1 minus 1 1 minus 1, something and these are basically your syndromes. And by looking at your syndromes, you will find out whether an error has occurred or not. So for example, this is a circuit which can be used to measure P1 tensor P2 tensor P3, where PIs are some poly. Nice. So we talked about how can we detect the error. So to detect error, it's simple. You basically just you measure your stabilizer operators. Now the logical operators, that's also very like easy to see in this framework. So for 3-qubit repetition code, like we had like 0 logical 0, 0, 1, 1 logical 1, 1, 1, and this was our state in the code space. The X bar that we chose was XXX and Z bar was ZII. Now instead of ZII, we could have also used IZI and IIZ, or or let's say ZZZ, and you could have used any of these here. Now, so you can see that there is an equivalent set of logical operators that you could have used, and actually using the stabilizer formalism, you can characterize this equivalent set of logical operators. So let's look at what are these equivalent set of logical operators. So let S be the stabilizer group. Let psi be a state in the code space. L be a logical operator. Then for any Sj which which is in the stabilizer group, Sj acting on psi will be psi. Now if you act on your Sj psi by L, that will be also L psi. So you see that if for L being a logical operator, LSJ is also a logical operator. So given a logical operator L, there exists a family of 2 to the power m operator LSJ that act equivalently on the code space. So basically the action of a logical operator is up to a stabilizer, because you can act a stabilizer and it will it's like nothing happened. Yeah. So a logical operator basically must belong to, the claim is that a logical operator must belong to the centralizer of the stabilizer group. And this you can see, so the question, so basically, how do we find, what are the logical operators? So basically to do that, you need to just, look at, so you have a stabilizer group and you need to find the centralizer, and then the question becomes, what is a centralizer? So you can see, from the Wolfram, I have taken this definition. So the centralizer of an element, Z of a group G, is a set of elements which commutes with it. So, all the elements which, which basically commute with it. And yeah, so you see that why it should happen, yeah, so basically, yeah. So the logical operator, it must commute with every element in the stabilizer group. If it does not commute, so let's say it does not belong in the stabilizer, in the centralizer, then basically it will not commute with the elements in the stabilizer group. And if it does not commute, then you can again show the contradiction that yeah. So for example, let's say L does not commute with some stabilizer Sj. So LSJ is, let's say, non-zero. So then we have LSJ is equal to minus SJL, because we are interested in Pauli operator. Now if you act on LSJ on some, let's say, some quantum state psi, which is in the code space, you get L psi. Let's call that psi prime. On the other hand, if you take minus SJL and act on psi, that is minus SJ acting on psi prime, that is minus psi prime. So again, you see a contradiction. So basically, you have your logical Pauli operator. They basically they must belong to the centralizer of the stabilizer group, and yeah, that's it. Yeah. So basically, this becomes quite simple, right? You just look at the stabilizer group, like generator. The generator basically gives you the group, or from the group you can also get the generator. So you just need to specify the generator, and that will give you the stabilizer group, and from there you can get the centralizer. And the distance basically is nothing but the minimal weight of any operator in the centralizer of the code. And why that should happen? Because the logical operators, they belong in the centralizer of the code, and the definition of distance is basically a minimum weight operator, like a minimum weight logical operator. And since the logical operator belong in the centralizer of the code, the minimum weight operator in the centralizer of the code will give you the distance of the code. Okay. So let's look at, like the 3-qubit repetition code. So here the stabilizer groups are basically, ZZI, ZIZ, IZZ, II, whatever. Centralizer, you can, like calculate, these are the ones. And you can see here that, like the minimum weight Pauli operator is 1. So, the 311 is basically, like the NKD notation for the 3-qubit repetition code. I mean, somebody could, like look at the 513 code, which is given by, these stabilizers. And so here you have like 5 physical qubit in code 1 logical qubit, and distance is 3. Like, you can just look at it here. Now, so that completes basically. Next week, I will talk about Tori code. Yeah. Thanks.
Hey, thanks, Kishor, for the tutorial.
So I think we have a